I think there are a couple of people that are on their way from the coffee place to come here, but we're going to start nevertheless. 4:31, so our final session today is on AI and data privacy and beyond, I guess. And I would like to introduce our session chairs. So Mauro SOZIO is Professor of Computer Science at Institut Polytechnique de Paris, Telecom. And Aleksander MADRY is Director of the MIT Center for Deployable Machine Learning. He's a faculty co-lead of the MIT Policy Forum, and is a well-esteemed colleague in my department. It's all yours.
So, hi everybody. So I would like to give you a warm welcome to our session on data privacy, AI and data privacy. I think it's going to be a very interesting session with two great speakers from MIT and two from French institutions. So we have a pretty tight schedule. So I'm going to hand it over to Aleksander, who is going to introduce the first speaker of the session.
Great. So welcome everyone. So first of all, I just want to say that if you have an option of having Patrick as a colleague in the department, please go for it. He's someone to really cherish as a colleague in many, many ways. But now, without further ado, let me introduce another of my great colleagues that I also very strongly recommend as having a colleague in the department, Marzyeh GHASSEMI. So Marzyeh is a faculty in the ECS department at MIT, and she really works on a very, very interesting set of topics. Essentially, she thinks about how AI as technology should and shouldn't be applied in the context of healthcare. And in particular, today, she will tell about some really interesting research that kind of talks about the privacy, which is something that we definitely care about in the healthcare systems, but also possible trade-offs that privacy entails. So without further ado, Marzyeh, please go ahead. And by the way, after her talk, we will have a Q&A with her. So just please think of the questions ahead of time. Marzyeh, please go.
Thank you. So I'm going to talk to you today about designing machine learning processes for equitable health systems. And I'm going to focus on some of the work that I've done with differential privacy. But to start, the space that I'd like you to be thinking in before we get into the privacy work is to set up why it's very important to check what happens after we use state-of-the-art techniques. So the data that I'm going to be talking about today is health data, which I call embodied data because it's from human bodies. And our goal in my group is to design robust, private, and fair algorithms. And this really requires diverse data sets for research use. Because if we want AI and machine learning to improve science and address medical harm that currently exists, we need better and more diverse data. My lab focuses on three things to try to create actionable insights in human health: figuring out how to build healthy models, that's robust, private, and fair, which often is more technical work; doing audits on the healthcare system using state-of-the-art methods, but maybe not designing anything new. So that's looking at what kind of healthcare is healthy. And then understanding what sort of interventions make sense in a healthcare setting, what behaviors are healthy. The first thing you need to know is clinical AI is here to stay. There are wonderful papers. These are just a few of them that show that clinical AI performs at or above humans in a range of tasks across the human lifespan. And so this isn't a toy anymore. It's something that it has a legitimate use case and is very helpful potentially in a medical setting. But when you look at this table from a fantastic paper Eric Topol did a couple of years ago, you'll see that the sample size N varies quite a bit. And the AUC, the performance number, is one number. There's only one number there. It's not broken down, for example, by gender, by ethnicity, by age, by national origin. And so we don't actually know for any specific person whether AI will work well for them. And this is just an artifact of the way that we tend to think about machine learning performance in general. But here, AI is learning from human practice, and not all doctors perform equally well on all patients. And so here's an example, just to set the stakes for you. We took the three largest chest X-ray data sets that are publicly available. That's over 700,000 images. And then we trained a state-of-the-art dense net, that's kind of convolutional neural network, to predict no finding. That means the model says the patient is healthy. And then we measured the false positive rate in different subpopulations. And we're going to call that the model underdiagnosis rate, because if you falsely positively say that somebody is healthy when they actually have a condition, they've been underdiagnosed. This is a problem because if you deploy a model that has a higher underdiagnosis rate on some subpopulation, like female patients, then that population would have a higher rate of no treatment if this model were deployed and you were not aware of this gap. So when we train these state-of-the-art models and make sure that they perform at or above what the current literature suggests in aggregate, just like in that table for the AUC, we find that they underperform larger underdiagnosis rate for female patients, young patients, Black patients, and patients on Medicaid insurance. And intersectional identities, for example, Black or Hispanic female patients, are underdiagnosed more than other identities like white female patients or the group they belong to, just female patients in general. And you might say, okay, this is a nice thing. I'm glad you told me. But maybe you have just pointed out a very simple thing, that we should just audit fairness in predictive models, and that should be published alongside. So this is one of the first papers I ever wrote examining the subclass performance for AUC. We found that there's actually significant differences in model accuracy by race, sex, and insurance type when we use ICU notes to predict mortality and psychiatric notes to predict psychiatric readmission. But it's not always this simple because we're now using high capacity models. So let's take, for example, the CYBERT contextual language model. And this is a model that's been trained to generate realistic text, which you may have seen examples of GPT-2 or 3 models, right? This is a contextual language model. But CYBERT has been trained on PubMed abstracts. So this is scientific abstracts that are publicly available. And it's a model you can download right now. I took a real sentence from a real medical note from a Boston area hospital. Blank race patient became belligerent and violent, sent to, and asked the model to fill in the blank. If I say Caucasian or white, the model fills in hospital. If I say African, African-American, or Black, the model fills in prison. And these models are being used right now for tasks like this, for note infilling, for question answering, for similar patient lookup. And that's just in the healthcare space, not to mention resume processing or student application screening. And this is not something we can fix later on. Other work that we published earlier this year at ICLR demonstrates that if you try to fix this downstream, so say that we have some biased data now, we learn this nice representation based on the biased data. And then, we throw that data away, keep the representation that the model learned, and fix the bias later on with perfectly balanced downstream training data. Well, the downstream training data is still getting projected to this representation that doesn't have good space, good separation for certain subclasses. And so even with perfectly balanced downstream data, we still see a gap in downstream task performance. And so this is something you have to think about now. You can't just fix it later. Because bias is part of the clinical landscape, because doctors are humans and humans are biased. So pop quiz, how bad is this? And these should be very hard. Can you tell if this patient is Black or white? You probably can't, because the doctors we surveyed couldn't, but a machine learning model can. And it's using some things that make sense. For example, in the United States and specifically in the Boston area, African-American patients have a higher rate of hypertension and hemodialysis. But it's also doing this really well across 2 hospital data sets in Boston and New York, using very simple features and models. And some of the reason that it's able to detect whether a patient is white is just if a doctor's comfortable commenting on their skin. And this is not something that's desirable. Same quiz. Is this patient Black or white? You probably can't tell because radiologists can't. We surveyed them. But a model can. It can detect patients' self-reported race, not their genetic ancestry, but what they say they identify as, with very high accuracy across many different data sets. And this is not BMI, it's not breast density, it's not bone density, and it's not disease distribution. We checked all those proxies. It's also not something that's present at one part of the frequency domain. This is something that even when you filter an image significantly so that it doesn't really look like a chest X-ray anymore, the spectral information is still obvious to a machine learning model. What does that have to do with patient privacy? Now that I've set up how easy, how trivial it is to figure out some private information about a patient, maybe I've motivated you and how easy it is to learn maybe these things despite proxies not being obvious to a human. Maybe you've said, okay, you really need privacy because we have some doctor that's looking at a patient's records, but only part of it potentially. And then we have a machine learning model that's going to make some prediction. And we don't want information, for example, about a unique patient like Sumano, who may be the only person of her gender, race, and age in her zip code, to be identifiable to some adversary who can access the data or the outputs of a model trained on the data. And so differential privacy is a state-of-the-art technique to protect people who have combinations of attributes that are uniquely identifiable, even if that data is legally de-identified according to some standard. And so differential privacy has really become a state-of-the-art, especially in industry where consumer privacy law dictates that you have to protect consumer privacy in these ways. In the research that we've done with differential privacy, we have found that there are significant differences in the utility you get in machine learning performance. And this is everything from logistic regression models up to GRU-based models. That's a kind of recurrent neural network architecture. And this is on a very simple task of predicting mortality year to year in the MIMIC data set. So you can see here, for example, what happens when we go from a logistic regression model that has no, and that's in pink, the dark line, differential privacy added, all the way down here to the dark blue line. And now it's doing almost no better than 60% in general AUC, which is incredibly poor. And I should say, predicting mortality in the ICU is something we're used to getting AUCs between 0.75 and 0.9 on in general in machine learning for health. It's one of those tasks that is considered almost solved. But when you add differential privacy, there's a huge trade-off in the utility that we see. There's another trade-off, which is adding privacy changes the most helpful group in the training data as measured by influence functions from Black patients to white patients for Black test patients. So when you have no privacy, no differential privacy, the most helpful ethnicity for classifying a Black patient is other Black patients' records. But you can see as soon as you add any privacy, it's only using white patient data. And that's by design. Differentially private learning, DPSGD, noises and clips data that is too unique in a mini batch. But in a healthcare setting, it's minorities that are too unique. It's an actual human that is an outlier in this data set. And so by design, it's removing the influence that minority patients have on learning classifiers. And that's what's destroying performance in minority patients when we do deployments. And this is not fixable without better learning and more diverse data. And so our recent work is focusing on a very strange thing that we noticed. So here you see that the difference between models actually becomes a little bit better in this really strange gray window for mortality performance. Why is that? This gray window is when the MIMIC data set changed its electronic healthcare records type. So it went from using CareView as its electronic healthcare record system to MetaVision as the EHR system. And that distribution shift is a setting where DP seems to actually improve performance as compared to just using a vanilla model. And our initial work in some imaging data sets like CFAR shows that, in general, DP models do a lot better, have a significantly smaller gap only under shifted settings. And so we wanted to see if we could use techniques for guaranteeing robustness rather than privacy. So here's a paper that we have an interesting result in. So we tried to benchmark all of these distributionally robust optimization models like group DRO and invariant risk minimization, many flavors of that, as compared to vanilla empirical risk minimization in healthcare data. And what we found is that it doesn't actually improve utility or robustness over traditional optimization, specifically in healthcare settings. But we know from other work that DP optimization does provide improved robustness, but it's at the expense of utility, right? So we have these two things. We know that DRO, distributionally robust optimization, doesn't seem to provide significant utility or robustness over traditional optimization of health data. DP seems to, but at the expense of utility, especially in certain subpopulations. And so our goal was to improve DRO with DP. So here, if we have data that's got a blue class majority group, and then there are a couple of different scaled minority groups, what happens when you randomly sample mini batches with DP-SGD is you get distributions that look like this. And so what that means is you're optimizing loss really here, just in the very center of your distribution. But we use an adaptive sampling algorithm from DRO work to try to create diverse batch sampling. This prioritizes the tails of the distribution as compared to random sampling. And so that results in optimizing tail loss as well. And what we find is that this significantly improves the performance of models because, and this is only in the shift setting, I should say, if you have no shift and your test data looks exactly like your training data, then you don't need to use something like DP. Because you don't need distributionally robust optimization. You don't have to worry about the new data looking any different from the old data. But realistically, we know that new data is going to look different from old data at some point. And so here we find that the DP addition to DRO does significantly better under shift conditions when we look at one health data set, the MIMIC3 notes, and then two non-health data sets, one from the wilds data set, and then the water bird spurious correlation data set. And this is really exciting because there are no simple fixes for ethical AI in health. This is an ongoing process that's going to require diverse data and diverse teams to think about this entire pipeline. And some of the things that we've talked about today are on the algorithm development side and on the post-deployment consideration sides for audits, and then trying to improve the way that we learn representations. But really, you're going to have to consider sources of bias in the data. This is not something where you can just make a machine learning model, have it work, say it should be private, and then let it go. That's actually going to do more harm than good. You have to evaluate comprehensively and recognize that not all gaps can be corrected. There are going to be some differences no matter what. What is going to be a clinically valid and acceptable outcome to look at? And machine learning for health really lags other subfields in reproducibility currently. That's because often there are restrictions placed on sharing healthcare data that are not always privacy related, but maybe more IP and paper generation related. And so this is also another area that I try to strongly advocate for. I think there should be more publicly available health data sets that are de-identified and available to researchers who are accredited. Because we can't just explain models to fix them. We need to understand the processes that generate our data and work towards data model and processes that are reproducible and transparent. This is work that was done with my Healthy ML lab at MIT. And thank you for listening to my talk on creating actionable insights in human health.
Okay, thank you. Thank you very much to the organizers for the invitation and to all of you for to attend this talk. So I'm going to talk about topics related to privacy, also related to the data leakage in machine learning software, so models if you want it. Just to show up, go back to the introduction. So we recently created this international lab between France and Canada, together with several institutions and CNRS, Paris-Saclay from the French side, and the ETS, Mila, University of McGill on the Canadian side. We are 15 permanent researchers, and we are growing up until 20. So we're very much happy if you want to visit us. So I'm going to talk about two topics. They are very much complementary to each other. I will give a different level of technicality. So one level is expected to be accessible to everybody, and there are some, from time to time, some slides that are a bit more technical. So the first part of my talk is going to be related to quantifying the membership inference information leakage in machine learning models. So this idea that you train a model and you release your model, but the model contains information from the training set about the data. The second part of the talk is very much related to what we saw before. It has to do how we can manage to learn representations that do not contain sensitive information about particular features, like biases or IDs of users, and so on and so forth, all right? So I don't need to tell you that we are plenty in the, I would prefer to call this a machine learning revolution, because it's a bit more related to my talk than AI, which is a bit too general as a keyword. But I would like to start with this motivation. This picture is taken from OpenAI, so maybe you've already seen this. In this picture, we see the petaflops per second times days on the y-axis as a function of time since 1960s. And this is showing us the amount of resources that we need to train a state-of-the-art model at the time. Okay, so what you can see that this was growing up with a doubling in terms of resources every 2 years, but since the last 10 years, we're just going even much faster. We're doubling almost 3 years and a half, 3 months and a half, right? So more importantly, and I think this is going back to a discussion that we had just with the organizers during the break, right now in these big models, we're training billions of parameters. Just to give you a rough idea, you can compare this one parameter equal to one neuron. So you could say that we are training about more than the number of neurons that you have in a rat. So this is sort of 100 billions of parameters, which also is important to take into account that these billions of parameters are, of course, storing a lot of information from the training data. Okay, that's the information they use to decide. Now, when it comes to define what machine learning is about it, well, some people will tell you it's a sort of advanced statistics, others will tell you a sort of pattern recognition model, others will tell you, look, a sort of biological-inspired technology, AI, and some accepted people will tell you, well, sort of glorified curve fitting, right? And it's maybe all of them together at the same time, but what is important to pay attention is that we have been programming computers for the last, I would say, 40 years, even more. But the next 40 years are certainly going to be about training computers, where basically we're making software out of data. So that's very much related to why I'm bringing this problem. So let me quickly and very simple go to the blackboard to easily introduce in a few words what is a machine learning model. So we have some nature that creates in an arbitrary manner that we don't know data. These are the features, image, sounds, speech, text, whatever you want to model. There is an object that also creates concepts in a probably random manner that are entangled with these features. And the goal of the learning algorithm is pick one possible set of billions of parameters in these days to somehow predict or to mimic the outcome of the object. Okay? So we need training data in order to fit those parameters, and we hope that when you go to the testing data, testing time, things will perform similarly, okay? Which is not always the case, but we cross fingers, and in all the data set that we have in academic, this happened quite nicely. In practice, it's another story. Now, this goal is what I would like to call imitation of the objects, because we're trying to mimic nature. There is a second problem that you can identify, which is the one of learning to approximate the object, which is quite different. It's something also very important these days. It's sort of information about the uncertainty that you may have in your predictions. But what is important to me in this talk is that all this data that you have, that you fit in the choice of this function, it's somehow going to help you to separate a structure of the data from noise, which is the magic of learning a classifier, but it's also storage in the parameters. So there is a data compression problem undergoing on there, okay? Now, this raises the obvious questions, is whether or not your data is saved, right? There are multiple different types of leakage in your data. The first one is, of course, when you provide your data, our data, to sort of a service provider that is going to use your data to build a model. Then you could access maybe that model in order to get a prediction. Can be done in a remote way via a cloud, or you can even get the software, the model itself, that you can run yourself. Okay? In all these cases, of course, you have a leakage of information, and that's why we need to take into account that as part of the model design. It's not new that you can learn a lot from the software itself, from the parameters of your models. Essentially, you can learn to reconstruct images from the training set, not equally, but up to some distortion. You could also identify IDs of less intuitive images, like the routine images, and so on and so forth. So this brings me to the first part of our contribution. So this is a joint work in two pieces. I'm going to talk about only the first one with Ganesh De Grosso, Georg Pichler, Marco Romanelli, who's here, Amit Chalasaid, and Katusha Palamesi. And this is about measuring the level of risk that you have in releasing your machine learning software, your algorithm. So basically, it's very well-known problem. So you have a training set that you use to train your model, and the question is, can you identify if a particular training sample or if a particular user was part of the training set? Okay, just by observing the model. Observing the model can go in two different ways. You can just have access to the black box model. You can carry your model without accessing the parameters of your model. Or you can also have access in a white box way to all the parameters, to all the inspection of your model itself. All right, this is what happens when you have the software of your model. This is what happens when you have access to a cloud to evaluate your model. Now, the obvious question is whether your data, the data you put in training set, is private from these two actions or not. Now, there has been a lot of work on this. I'm not going to go over the literature, but the path that we're going to take here is quite different to what has been done before. So the idea is to have a very simple tool to check, there's a sort of sanity check before you release your model. So what you're going to assume is that a potential attacker will have access to the model itself, will have access to carrier model as many times as he wishes, but doesn't have access to any additional data. Okay? The second part, having access to additional data, is a second extension of this that I'm not going to talk about here. But in this setup, the attacker has access to a testing sample, the sample and the concept, the class, and knowing the model is intending to compute sort of a score from which he wants to detect if this particular sample was or not in the training set. Okay? We call this membership inference attacks, and this is important because if you identify that, you can learn things about that particular sample out of that. Yeah. Now, that's very simple, but of course, the problem comes into finding this function. And here's the simple idea that we're using to do so. Suppose that we're giving with these two classes training set, very simple. So we have samples here, this is one class, and we have samples here, this is another class. There is a boundary decision region, that's the optimal one that we don't know, but we train a classifier for this binary classification problem, and we come up with this suboptimal but still quite good decision region. Right? Now, the claim is that the testing samples, those that we haven't seen during training, those that are not in our training set, are not going to be very deep in the decision boundaries, but they're going to be close to the borders of the decision boundaries. Well, this is okay. Maybe I should get far away. Okay, now it's better. They're going to be close to the decision boundaries, right? Now, the idea of this is the following. If we are able to measure how far we are from the decision boundaries, then we will be able to say if these samples were or not in the training set. How we're going to do this? Very simple. We're going to use an adversarial attack, a very simple model. So we're going to perturbate all the samples that we want to test, and we're going to measure how large the perturbation should be in order to change the decision to the other side of the decision boundary, right? And get a classification error. If things were as we expect, the samples that are not in the training set will require very little noise compared to the samples that were in the training set, right? That's the simple idea. And indeed, this has happened in that way. Here we have an histogram of what's going on when you basically do this on training samples that were in the training set and testing samples that were not in the training set. We're plotting the level of the noise. I'm going to tell you right away how we measure that. And you see that the testing samples are mostly on the left, which means that we need to add a very little noise in order to create those adversarial perturbations. And for the training samples, we need to add a much larger noise. Of course, there is a superposition. It's not perfect, but it still is quite well separable. And this is how the algorithm looks like. In a few words, by looking at the picture, we observe a testing sample with a class, the learning algorithm that we're using. We basically we add noise to create an adversarial perturbation, the minimum that we need in order to change the class compared to the clean prediction. And then we say that if the level of the noise is small, then clearly it's not a member because it was too close to the decision boundary. If the level of the noise is larger than some threshold, then it is a member. Okay? So how we measure the level of the noise, we just take the LP norm. There are multiple ways of doing this. We have tried also different ways, but this was very much working well. Now, I'm not going to go on details on all these results, right? But just quickly to show you, for those of you that are familiar with this topic, is that here we have, the different networks, Cypher 100, two ways of measuring the errors, the ROC, which is the area in the operational decision region, and the accuracy of the detection of these membership inference samples. And basically, you see that compared to all the models that are not using additional data, what we propose, which is very simple, outperforms clearly, and is very much close to the best that you can get, even though there are still gaps and, to reach. And compared to models that use adversarial data, extra samples to learn the attacker, well, in some cases, even better. In others, it's similar. In others, there is still a gap to reach. Well, that's the ROC's curves that I'm going to skip. Now, this brings me to the second part, which is a very different problem. It's the situation in which you need to share your data, or you want to sort of satinize your data, remove bias from your data. Okay? Was exactly related to what we were discussing before. So you have your training data that is ready. You want to share that, but you want to remove sensitive features, sensitive attributes from that training data, or you want to remove biases from that training data. Okay? So the way we could do that is we could learn representations that basically make the representation data completely independent of the sensitive attributes. I'm going to talk about this. This is a joint work with Georg Pichler, Pierre Colombo, and Malik Boudiaf and Gunther Kollinger. So here's the problem that we're looking at. We're given with a training data. There are 3 entries in these data sets. X is simply the features, speech, audio, text, whatever you want to treat. Y is the target label that you would like to predict. You're training a model for one reason. That's the reason, is to predict Y. And Z is the sensitive attributes, the identity, for example, of X, or the race, anything that you would like to remove for your data. So this problem is the following. We want to treat this data in such a way that we learn representations of the data that preserve as much as possible information about Y, the target label, and as little as possible information about Z, right? The label that you would like to remove from your data. Then you can train a model after that without the bias if things went okay. Now, the optimal way and the most natural way of doing that is to use information measures, and in particular, mutual information. Mutual information is a universal measure of dependence, measure all higher orders of dependency in statistics. And basically, the idea is that you will train a model that creates representations that are as much as correlated or carries as much as information as possible with respect to the target label, and that minimize the mutual information between the representations and the sensitive label, the sensitive attribute that you would like to remove. Yeah, that's very natural, but of course, things got always a bit more difficult, is that learning this mutual information, which decompose into the differential entropies, right, is in general hard. It is well known to be a very difficult problem. It's very difficult to learn to have estimators that are differentiable, that learn entropies, differential entropies, with confidence, right? That's a challenging problem. This is why the first part in this in this research was to come up with estimators for which we have confidence to estimate the differential entropy. Now, I'm not going to go on details on this. I'd be happy to chat during the questions if you're interested in that. But it's very simple. We take an empirical average using samples of the log likelihood of some model. And this model is a simple kernel, but with some tricks, as usual. This simple kernel is a mixture kernel of Gaussian kernels, in which we train the weights of the mixtures and the covariance matrices for each sample and the uncles of those Gaussians. Right? This is what we do. This performs well. This also extends to conditional entropy, and by estimating conditional entropy, you could also estimate mutual information by taking the difference. And this is what we have done here. And here I just show you a very simple example of a fair classifier we were discussing before. Suppose that you are given with a text data set in which you have two possible target labels, the sentiment and the mention that you would like to preserve in your data after the representation learning model. And you would like to remove information about a sensitive attribute, which could be the race, which is the case here. So here, if you plot how much success, how much information you have left after learning the representation model to predict the target task as a function of lambda, when lambda increases, you enforce more the disentanglement, so you remove more and more information about the sensitive feature. You see that the naive estimator that we're using basically preserves full performance, compared to many other competitors that I'm not going to detail. In the case of the private task, the accuracy, it goes down until a random and perfectly random guessing classifier. Okay? So the same thing happens with the other task of mention, and we have a lot of experience on many different types of data. It seems to perform very well. Okay? So let me go to the conclusions. So I think it's a very exciting time to work in the field of machine learning because there is a way to make high level or large scale impact in society. But all these models with billions of parameters capture a lot of data. That data can have bias. That data can be sensitive. So of course we have to take care to sort of evaluate before releasing those models, right? We need to have evaluation metrics. The tool that we're proposing here for the membership inference, it seems to be good. It's not perfect, but it's good, simple to use, and outperforms the state-of-the-art methods, and is very convenient. We're having extensions to extend this to incorporate a powerful attacker with data, mostly based on the recent work that we did using differential geometry tools. And related to the naive estimator, is very efficient in learning to disentangle representations, but it's not enough to prove that there is no information left in those representations from a legal viewpoint. So this is very much open. Thanks to all of the students and collaborators that work with me under these different projects. I just talked to a few of them now, but there are many others. And thank you for listening.
So next speaker maybe doesn't need further introduction. So Aleksander MADRY, who is also a co-chair of this session, is a director of the MIT Center for Deployable Machine Learning and faculty co-lead. So let's hear.
Thank you. So yeah, I don't need any more introduction because I already talked too much. So So welcome everyone. So what I want to talk about the aspect that actually, if you pay attention today to all the talks today, you see that always shows up. Namely, the question of data, and in particular, how can we rely on data, and essentially, how difficult it is to make reliable inferences on data using a machine learning toolkit. Okay, so just in case you do not realize, is that just to remind us, it's just like machine learning is a really exciting field with a lot of successes. So we kind of have all this cool stuff, and again, I cannot overstate how exciting I am about everything that happens. So of course, each time I go somewhere and talk to people who are not computer scientists, they want to restart my computer, but no. I pressed cancel. Oof. Oof. Okay, I don't know what's happening. There is a sabotage happening. So anyway, the question there is, are we there yet? Yes, like I know they want to say, okay, so I'm reading in newspaper about all these advances. So essentially, is everything that is just left is just to, polish stuff, scale up, but, we essentially are there. So my short answer to that is no, and there's many reasons why the answer is no. Again, doesn't mean that we're not making progress, but we definitely are not there yet. But today, I want to focus on one aspect, namely on this kind of something that I really view as a key challenge in making machine learning make a real and kind of positive impact in the world, is namely understanding and modulating the role of data in machine learning. Okay? So in particular, if you are a machine learning researcher, you have this very cartoonish view of like how machine learning works, is that like you have some data, you put it into the model and you steer and train, and then you get your beautiful AI. And kind of as a result, much of the work is really focused on like, well, how does this model look like? What architecture we do? How do we train it, and so on? And this is important, like, don't get me wrong. And actually, it was the critical piece we needed to get this AI working. Like, that's what deep learning revolution was about. But kind of it's also somewhat an easier thing to do because it's easier to iterate on this architecture because you just like choose new architecture, you train it again, and see what if whatever you wanted to do happened. But as much as this was important and it's easy to do, well, there is this data aspect that I think is really still underexplored. Okay? In particular, there are two questions in the context of this session that I would like to highlight. So one of them is, essentially, as we already discussed, essentially Pablo, Marzyeh, that these models extract a lot of information from the data that we feed into them. Not all of this information we want them to learn. So how do we kind of restrict that? Like, how do we make sure that like it doesn't extract information we don't want them to extract? But the other question is also kind of, there is this question of, okay, so there is signal in data. And, and again, machine learning models extract it one way or another, like whatever that they find useful in this data. How do we harness this signal? How do we make it actually, be kind of lead to the outcomes, to the kind of, decisions and kind of functionality that we actually view as, genuinely positive? And today I will focus on this second question. And very fittingly, the previous two talks address the first question. So everything is completely coordinated. There are some very, very organized quarters kind of organizing the session. So essentially, so why do I talk about this? Because there is something very important to understand about how the machine learning models work, that at least the models that we have, is that essentially like the way machine learning models see the data tend to be very different to how we do see the data. So this was kind of something simple, but kind of quite surprising actually to me, at least when we kind of discovered it. So essentially, like imagine that you want to train a model to distinguish between dog and cat's pictures, and you think, okay, well, I know how you do it, right? Like to be able to distinguish, dogs and cats pictures, you need to kind of figure out these features like, the snout, the shape of an ear, the kind of, the fur, the texture of the fur, like all of these things, like if you look at the picture, I will know this is a picture of a dog and a picture of the cat. But that's how we as humans solve these tasks. It turns out that actually the way the models solve this task is completely different. Like the way they recognize what is cat and what is dog is completely foreign to us. It would not make sense to us, but it actually works. So kind of there is this very interesting phenomena of this like human ML misalignment where kind of, well, we have this model which solves this, very well, this cat versus dog task. And the logical jump that we make from this saying, oh, if it solves this task that I as a human to solve, I need to learn these particular features, well, then the model had to learn the same features. And that's actually completely wrong. So imagine kind of the analogy that I like to use here is like imagine that you are a professor and there is a student in your class who has zero interest in learning anything from your class. They just need to pass the exam. And yes, of course, one way to pass the exam is to actually learn all the material and pass the exam. But if the student is particularly smart and particularly lazy, what he or she might do is saying, oh, well, let me look at the past exams that were kind of put in front of it. And I think, oh, Professor MADRY likes to kind of ask about this part of the material. So, and never asks about this part of the material. So I don't need to learn that. And also whenever there are like the multiple choice tests, like he likes to go for like A, B, and C in a sequence. So you start learning these patterns. And it's kind of crazy, but it actually might work to get a very good score at the exam while learning very little. And this is exactly like this kind of lazy student, super smart but lazy student should be exactly the way you should view the machine learning models. So yes, we put a task in front of them, but just that they solve the task doesn't mean that they learn what we intended them to learn. And this alignment of this human ML alignment has a lot of consequences, and it kind of shows up everywhere. So when I personally kind of encountered it first is in this context of adversarial examples. This phenomena of surprising brittleness of state-of-the-art machine learning model classifiers that actually Pablo mentioned in passing. So what's adversarial examples? Well, adversarial examples, here is an example. So what we have here is this beautiful picture of a pig. That state-of-the-art model recognizes a pig with 91% confidence. So everything works exactly as intended. But now, something funny happens if I add just a little bit of noise to that image. It's not a random noise, it's a carefully chosen noise. But the point is that this is like really a tiny amount of noise. It just has very small and infinity norm. So you can't even tell the difference between the original image and the image after. And what is the funny thing that happens is that, well, to us, on the right, we still have this beautiful pig over there. But the model now believes this is an airliner with 99% confidence. So again, AI is magic. It makes pigs fly. So that's clearly an achievement. But that's not what's really happening. And this is just me playing with some pixels in computer in a laboratory setting. But it turns out that these things actually they are real. So a bunch of students at that time undergrads at MIT. Now some of them are my PhD students. That's what you need to get into my group. Is essentially they 3D printed a turtle that again is a turtle to us, but classifies as a rifle to a state-of-the-art classifier. They were thinking first of 3D printing a rifle that classifies as a turtle, but then realized that might not be a good idea. So that's where they stayed. And then there's kind of other stuff you can do. You can like print out, T-shirts that essentially make the object recognition models like be invisible to them. And essentially, so these things are real. And kind of the underlying reason for why these things happen is that yes, these perturbations that I apply, they are invisible to us, but they actually are in some ways very visible in the spectrum that the model pays attention to. So yes, so nothing changes to us, but a lot changes to the model, and that's why kind of it's its own. Now to it is the airplane. It's not a pig anymore. So this is kind of just one example of this challenge of like the model seeing something different than we. So the signal they extract from the data is different signal than what we think they might be extracting. And this shows up in other contexts, in context of data poisoning, where I can modify, I can plant some kind of spurious correlations in the data to make my model essentially rely, like make its decision process rely on something that I can completely control, that would not make sense to a human. And then essentially like this questions of reliability in the context of healthcare where kind of it turns out that like for instance the model to pass essentially this is just an example of a model that was supposed to recognize the condition based on X-ray of a patient, and it was doing very, very well until someone actually tried to look a little bit closer why, like what is it basing its decision on, and in particular to highlight the places that are kind of most important for the for the model's decision. And what they realized once they kind of took a closer look is that what the model was really looking for is the pen marks that the doctor was making when annotating the X-ray. So yeah, the model was doing very well. It was solving the task you put in front of it, but essentially it was not solving the task you wanted it to solve because it was not seeing X-rays. It was just essentially looking for pen marks and makes a basic decision on that. And like Marzyeh said about this, like detecting the race from this picture, even if they are completely blurred to us, it's exactly the fact is that the race is encoded in this other part of the spectrum, not the one that we perceive. Okay. So this is, so this is important. So essentially, there is this signal in data that we might not see, and because of it cannot modulate. And you can try now to think about like how to kind of hide this, essentially like okay, so maybe this model will learn something that they should not do, but maybe will protect, and that's something that Pablo mentioned a little bit. And the message is that maybe I will lock my, I will encrypt my, my network, and essentially that's how I will make sure this happens. And the answer is that none of these things really really work. Like essentially, you can access, you can interrogate the model, and you can manipulate the model through this like invisible spectrum. Even if you have no access to the model, kind of physical access to the model and the way to to manipulate it in any way. Okay. So, okay, so these are kind of the bad news, that there is this kind of misalignment, and it leads to a lot of kind of problems. Again, problems that Regina was talking about, and essentially, again, problems that really are, this is what really is stopping us from really deploying machine learning in a responsible way. So what do we do? Well, that remains to still be an active area of research, but I would say that there are like 3 conceptual steps that at least, I view we should be pursuing in this context. So the first step is kind of trying to find a systematic way to map out some of these vulnerabilities, like some of these things that kind of the model go differently than we do. So again, there's a lot of body of work here, but essentially, in some of my group, part of it is just getting a simulator that you can actually use to really create unusual inputs and seeing what happens. So for instance, you can have a cup with different textures, and seeing if the different texture will really sway the prediction of the model, and the answer is yes. Or you can, of course, have a variety of interrogation techniques when you kind of try to surface the features that really the model uses for predictions, and trying to see in a causal way, which one are the right ones, and seeing if they are if they are the one that they really should be there. So that kind of allows you to guide the debugging. Then the second step is to, so you can interrogate the model by providing it with different inputs or trying to look at its features, but you also should understand data. Okay, and what this means is that in particular, you would like to take a look at the data, but not, again, from the point of view how the data looks to us, but actually from the point of view how the data looks to a model. In particular, what inputs are similar to the model as opposed to us. Essentially, there is a technique, for instance, the whole framework, that allows us to exactly ask these questions, kind of find a way to really understand the structure of the data, again, the way the model sees it, as opposed to the way we see it. And the third one is saying, if we understand, what is the problem with the model, what are the biases in the data that we might want to not like, and essentially, what is data telling the model that we don't want the model to actually learn, we can kind of imbue different kind of robustness in the model. So we can either provide some invariances during training, saying, this kind of, for instance, this adding small noise should not be swaying your predictions too much, and kind of this is some kind of invariance property. Or you can do something even cooler, is trying, this is work actually with Antonio over here, is trying to edit the model. Essentially, for instance, imagine that your model there was this example of the cow on the sand. So imagine that, well, here there is a car on the tarmac versus car on the snow, but the point is that, yes, imagine you have this model that recognizes cars when they are on tarmac in natural condition, but they completely think this is a husky if it is is a car on the snow, because they only saw snow in the context of huskies. Well, what you can do is you can essentially edit the model, do a surgery, brain surgery on the model, and tell it, look, actually snow is the same as tarmac, so it should not really matter. So you can kind of merge these 2 concepts or swap these 2 concepts, and from now on, the model not only recognizes this picture correctly, but actually all the pictures with kind of similar spurious correlations from now on are doing better. So you're kind of doing this brain surgery to kind of correct this misconception of the bias there. And there are also other approaches in this way. Okay, so these are the 3 steps that you can take to kind of mitigate the problem of this kind of misalignment of the spectrum that the models pay attention to versus the humans. But actually what is cool is that there is actually a way to not view this as a weakness, but actually view it as an advantage. Okay, and the idea is a bit crazy, and kind of it goes back to this idea that, why is the stop sign looking the way it is looking? Well, first of all, we want to make sure that we always are able to see it no matter what the condition. Is it snowing? Is it kind of very sunny? So that's why it's a different shape. That's why it's red. So this is a color that we tend to see very well. And kind of that's why we decide, we want humans to be able to see it reliably. So this is how we design the stop sign. Well, but how about the design of the stop sign if you wanted the machine vision models to see it reliably? What is the right design for that? Well, essentially, in our paper, we showed that there is a way to kind of create, essentially use this spectrum that the models see and kind of create objects that can be recognized reliably, in this spectrum. So essentially, we make it easier for the machine vision model to see objects reliably in kind of non-adversarial noise and so on. So we are kind of trying to lean into the way the model sees the world as opposed to the way we see the world. Okay, so this is really cool, and there's a lot of kind of nice demos that you can do with that. Okay, so that's all I have to say. And let me just quickly conclude. So, one thing that I really want to, reiterate is that like data is the most critical aspect of ML. Again, models are cool. They have a lot of parameters, and this is all very, very cool. But in the end, it all goes back to data. And again, if you hear what Marzyeh said, Regina said, everyone said, data is really like what makes and breaks machine learning, because that's where we are getting the signal. That's where we get the model of the world from. And so, yeah, so if you use ML, you really need to think through how it uses data. That's what you need to understand. And this involves also thinking about both privacy, so essentially, are there things that they should not be extracting, and this robustness, meaning which I really view the misalignment things. Is it seeing the world the way it should, that is aligned with the goals that we have for it? Okay, so essentially, this is not coming easy. This is not something that you can just fix with like one, objective function that you just write down, or with the one canonical data set. So essentially, you need to develop a whole toolkit, and most importantly, practice of doing that. Okay, so practice means that yes, on one hand, the ML researchers have to actually embrace the complexity and messiness of real-world data and tasks. And again, some of the people that spoke today, they actually are very much doing that. But also there is kind of, on the domain practitioners, they really need to work with us to help clarify the goals of like, how the data was generated and what they are trying to accomplish. So that's in the healthcare setting. There are all these crazy things about that. You train a model, and for instance, one of the predictors of a particular condition is whether a particular, like, the measurement of the, of the blood pressure was taken or not. Not what was the value of this blood pressure measurement, but whether it was done or not. Why? Well, because essentially, if you come to a hospital, they will measure your blood pressure only in certain conditions. So just the fact that this measurement was made, it meant that the nurse or the doctor who was seeing the patient realized there is something there, and that's why they had to do check. So that's fine. This you can model for. But now imagine that different nurses or different doctors have different practices or different rules of thumb when they actually make this blood pressure measurement or not. Imagine what it does to the robustness of the model and applicability across different settings. So again, if the doctors realize that this is important to have like the same standard, well, that would help a lot, because then we will understand, what the data is generated in a fairly consistent way. And of course, again, the question also is like, what is the objective? Is saying, like with this example of this pen marks, kind of, like what is the real objective there? It's not just to give the right answer for this particular X-rays, but doing something deeper there. And articulating this will require domain experts there. So this goes way beyond the technical question, but there is, I think, a really difficult question of like, how do we organize it in society? Like, it's not something you can just throw over the fence. So, oh yeah, the machine learning researchers would develop the school models and then throw it over this fence to the practitioners, and they will kind of figure it out. And it will not be also the other way around, saying, oh, we need ML to just, here's our data, come back with a model that works. So I don't think this mindset is really like, kind of that we need to work together is that much imbued, like kind of, and that much popular. And I think there is a big policy question. How do we actually go towards that? And again, this is difficult, like to train the personnel to do consistent measurements of like, or when they, when there is an incoming patient, that's money, that's training, like where is this money coming from? Anyway, I will just stop here and yeah, thank you.
Okay, right, so the next speaker is Renaud. Sorry if I mispronounce your name. So he's a research director at CEA, right, which is the French Atomic Energy Commission. And he's going to talk about homomorphic encryption. Thanks.
Okay, so we have this. Okay, so good afternoon, everyone. So, so I'm doing research in cryptography, basically. And I must admit that in cryptography, so there is a community of people who are trying to bring back AI 10 to 15 years back in the past, but we are trying to do it directly over encrypted data. And we are doing this with a new tool or a new toy that we developed in the cryptographic community around 10 years ago, which is called FHE for fully homomorphic encryption. So fully homomorphic encryption is cryptography. So cryptography is basically mathematical machinery that allows to turn plain text into ciphertext, usually with the knowledge of a public key, and to go in the reverse direction, so get back from ciphertext to plain text with the knowledge of a secret key. With homomorphic encryption, we have also operators that works over ciphertext, and which allows you to produce new ciphertexts which are meaningful with respect to some computation with respect to the plain text domain. So basically what homomorphic encryption allows is to perform calculation directly over encrypted data without, like it's software only, and it's just mathematical security. So basically we can send, oh, it's not pointing. Yeah. So for example, we can imagine setups where Alice will send homomorphically encrypted data towards a distant platform or a distant cloud, where Bob can also send encrypted data under the public key of Alice. So Bob or many Bobs can be a data provider. And then the cloud will be able to evaluate some function directly over this encrypted data and to produce results, being either intermediary results or final results, which are only accessible to Alice in the sense that she is the owner of the secret key. So just to convince you that it's just not dark magic, I have a very simple Hello World example. So for example, if we consider the Palier crypto system, then we associate a ciphertext C to a message M via an exponentiation modulo n squared, and n is the product of two large prime, okay? And so what's happening now, if I'm sort of multiplying two ciphertexts together, then as we know since kindergarten, then the exponent will just sum up, right? So by doing a product in the ciphertext space, I get addition in the plain text space. And addition is a special restricted kind of calculation. I will spare you the detail of like the more complex mathematical machinery of fully homomorphic encryption, but we're able to build, also relying on different mathematics, we're able to build crypto systems that will provide us with both operator, multiplication, and addition over encrypted data. And thanks to the magic of theoretical computer science, this is enough to achieve Turing completeness, which basically means that if we have a crypto system supporting these two operations, then we can, at least in principle, execute any algorithm directly over encrypted data. You may have heard about fully homomorphic encryption, and you may have been left with the idea that it's something that's so computationally costly that it is useless in practice. So that was true of the first theoretical construction that were developed 10 years ago, and basically it was the answer of a theoretician to a 30-year-old conjecture. So the sort of computational overhead were all polynomial in the security parameter of the crypto system, but the polynomial were having like too high degrees to be of any use. Of course, we've been working on this efficiency issue very hard since basically this Craig Gentry showed that it was possible. And what we have achieved is not cheap homomorphic encryption. This is still a computationally involved set of primitives, but we have achieved, let's say, non-prohibitive efficiency. So if you really need homomorphic encryption to achieve your security objective, and if you find a way of using it, of optimizing it, and of using it as parsimoniously as possible, then it becomes useful. And I will try to convince you of that. And also in the community, we've also worked on developing like tools like compilers that allows you to basically realize the promise of homomorphic encryption, which is to execute programs directly over encrypted data. And we're also working on developing standards for homomorphic cryptography, which is something very important for its applicability. At present, the trend in homomorphic encryption is to make the distinction between two approaches. One is the generalist FHE approaches, in which we have like no restriction on the kind of computation, on the kind of algorithm that we can execute over encrypted data. It's nice because there are open source compilers in the community, so you can just easily have stuff running in the encrypted domain. The issue is that it's costly. It's costly also because we have to like split a calculation nearly down to a logical gate level, which we run homomorphically, and that means a lot of computation. So this approach is targets mainly a situation in which either you have a low volume of computation to do in the encrypted domain, or you have very mild latency constraints. However, we also worked on many algorithms. And what happened most of the time is that we realized that the mathematical structure of our crypto system gives us a lot of degrees of freedom, and that we can tweak or tune them in order to gain 1 or 2 order of magnitude of performances when evaluating a specific algorithm. So, of course, it would not be cost effective to do that for any algorithm in the world. So that's why perhaps 5 years ago in the community, we started to look for algorithm to which we could specialize homomorphic encryption and which would have some sort of wide spectrum of applications. So, so we turned to a machine learning algorithm and try to see if homomorphic encryption could help in addressing a number of confidentiality or privacy questions around it. Like, for example, if you have an existing machine learning model, can you have it run over encrypted data in order to sort of preserve the confidentiality of the input data, of the user data, and of the output of the machine learning model? If you want to build a model from several databases, can you do that without disclosing these databases? Because there's a lot of value in the data themselves. And in doing so, we also gain a better understanding of the kind of machine learning operation or operators that are perhaps more suited to be executed efficiently or as inefficiently as possible over FHE, and perhaps the next step is also to sort of give this knowledge to the machine learning community such that you have an idea of the kind of things that works well over encrypted data. So if we get back to Alice, Bob, and so on, but try to instantiate the scenario over perhaps in a machine learning setup, so we can imagine having a patient sending encrypted data with the public key of its doctor towards a server, and that server will just run the machine learning model over the encrypted patient data. So all the intermediate data will then be sealed under the homomorphic encryption layer. And it will produce a diagnostic that only the doctor of, well, the owner of the secret key, I don't care if it's a doctor or not, can decipher. So this is not science fiction in the sense that, for example, we've been able to demonstrate using an embedding-based neural network, we've been able to demonstrate what I would consider an advanced machine learning function, but I'm not a data scientist. So, but we've been able to perform, like, for example, encrypted domains speaker recognition in near real time by integrating fully homomorphic encryption into the Vox Celeb speaker recognition system. So there are a number of things that are starting to work. So why does it work? It basically works because we are also able to partition the overall computation between some stuff that is done in prior encryption in the plaintext domain and stuff that needs to be done, computation that needs to be done in the encrypted domain. And the advantage of using embedding-based network is that their job is not to take decision, it's to generate convenient representation And so basically what needs to be done in the encrypted domain is the matching between the two representations, which is much smaller than running the full network. And that then you can do with some sort of a second classifier that is either a small neural network or even things as simple as one nearest neighbor classifier sometimes are enough to do the job. With respect to training, so we can consider scenarios, for example, where we have two entities, say they are owning like databases of cyber attack signature, and they want to train a global model on the union of their two data sets. But because these data are very sensitive, they are not willing to share them with one another, and they are neither willing of sharing them with a server. So fortunately, in the machine learning community, you've been developing a number of protocols to collaboratively train models. And one of these protocols, for example, is federated learning, where a central server starts with an arbitrary model, sends it to the clients, which are owning the training data. So the client then do a few iterations of a training algorithm, send a model back, model is aggregated and sent back to the client, and so on. So the good thing about this kind of protocol is that the training data remain on the client side. So that's good. But as was discussed in the previous talk, if the server will see model updates or even just the final model, then there's a lot of leakage on the training data. So it's perhaps not as worse as disclosing the data, but there's really a lot of leakage. So in that case, we can have the server running in the encrypted domain using homomorphic encryption. And what that basically means is that the server is completely blindfolded. It doesn't see any model updates. It doesn't see the final model. So it is basically completely removed from the loop in terms of confidentiality or privacy of the training data, which is of course an interesting thing. The good news also is that if we consider at least the basic aggregation algorithms that are used in federated learning, then it's like simple FHE computation. So it's things that we can do efficiently, and of course the models are big, so there's a large volume of FHE computation, but there are simple ones. So, okay, when I'm saying large model, I'm saying model with, say, 500,000 parameters. So that may mean very small to you, which is, but that's the kind of things we're able to achieve. And for example, we've been able to run some experiments where training such a model on the FEMNIS dataset, for example, bringing homomorphic encryption onto the server would add only 6% to the overall duration of the training. Okay, so that's reasonable, and it is also explained by the fact that the training computation time is mostly dominated by what's happening here. Okay, there are other approaches that works well with like collaborative training approaches that works well with homomorphic encryption, like the private aggregation of teacher ensemble of Papernot and al., which is also interesting because the homomorphic calculation that needs to be done are more complex, but it is independent of the size of the model. The volume of FHE computation depends on the number of clients and the number of classes, and not on the size of the model, which is a nice property if we want to try scaling to this kind of approach to larger model. Okay, still, I'm not here to oversell FHE in the sense that FHE will not be the solution to any security issue you may have in AI or machine learning. And basically, FHE address first only confidentiality threats, that's the first point, and confidentiality threats that come from the server. So that's good, that's nice, but that's only one facet of the problem, because confidentiality threats may come from other clients, may come from the entity to which you disclose the final model. So in complete system architecture, you have to, homomorphic encryption won't be enough, and you'll have to associate it with other countermeasure, as we say in the cybersecurity field. And one one countermeasure, which is very important, is differential privacy. And what's interesting from a research point of view is that it's not just saying, okay, let's do FHE with differential privacy. FHE will come with some constraint. It will impose discretization, bounds on the noise that you will be able to add, and this kind of disrupt the differential confidentiality bounds that we have to compute. So what is basically interesting is that we have to design differential privacy for FHE, or interworking properly with FHE. So just to start concluding, so yeah, so the main point I want you to take away is that basically with respect to inference or training, there are a number of things that are already practical in terms of using FHE for improving the confidentiality of inference or collaborative training. And also, there are also interesting research in the sense that scaling to the evaluation of really large model in the encrypted domain is something that is very challenging. So you've understood that so far we've sort of worked around that issue with a careful partitioning of what needs to be, of the computation that needs to be done in the encrypted domain and those that can be done meaningfully in the plain domain. And also in terms of training, well, the community or the machine learning community is imagining a lot of new aggregation rules that have the kind of properties that you want, and for example, aggregation rule like CRUM, which have some nice Byzantine resistance to data poisoning threats. This is the kind of things on which we have to do more work in order to be able to run that over fully homomorphic encryption. So yeah, so as I was saying, I'm from the crypto community, so maybe I come a little bit like a guy who has a solution and who is looking for a problem that it solves. So that's probably true because in FHE we've been looking for some kind of killer app for a number of years. But at least machine learning machinery seems to be an interesting app, an interesting setup to which FHE can be meaningfully applied. And yeah, as a key takeaway, so we feel that there are a number of practical application scenarios in which homomorphic encryption can be applied, and also a lot of interesting questions to be looked at. So yeah, there was a bunch of references, and thanks a lot for your attention.